fundamental definitions about fuzzy time series. I'm going to talk about how artificial neural networks can be used in fuzzy time series approaches to determine the relationships between observation of a time series. After that, finally, I'll give the implementation and the obtained results. Such as temperature and share prices of stockholders contain some uncertainty in itself. The conventional time series analysis can produce unsatisfactory forecasts for such time series. So Song and Chisholm first introduced the definition of a fuzzy time series based on the concept of the fuzzy theory proposed by Lütfü Askergari. Fuzzy time series forecasting models have drawn a great amount of attention in recent years, and various models have been proposed. As I mentioned before, the definition of fuzzy time series was first introduced by Song and Chisholm, and in here some basic concepts of fuzzy time series are briefly given. Let U be the universe of discourse, and a fuzzy set AI of U can be defined as in here, where FAI is the membership function of the fuzzy set AI, UA is a generic element of the fuzzy set AI, and this function represents the degree of belongingness of UA to AI. So we can give some definitions, some fundamental definitions about fuzzy time series. The first definition is about a fuzzy time series. Let YT a subset of real numbers be the universe of discourse by which fuzzy sets FT are defined. If FT is a collection of F1T, F2T, and so on, then this FT can be called as a fuzzy time series defined on YT. Second definition is about the fuzzy relationships. And these relationships assume that FT is called only by FT minus 1. Then the relationship can be expressed as like in here. Let FT minus 1 equals to AI and FT relationship between FT and FT minus 1 can be given as in here AI to AJ. Then we can make a definition of a fuzzy time series forecasting model. In the third definition, you can see, let FT be a fuzzy time series, is FT is caused by these elements, FT minus 1 to FT minus m. The nth order fuzzy time series forecasting model can be given as follows. Like in all the fuzzy systems, fuzzy logic-based systems, fuzzy time series approaches consist of three main steps. In the first step, which is called fuzzification, observations of a time series are mapped into fuzzy values, which are fuzzy sets or fuzzy numbers. In the next fuzzy relationships between the observations are established then by using these relationships, fuzzy inference made. In other words, fuzzy predictions are calculated. And in the last step, which is called the fuzzification, obtained fuzzy observations are mapped into real values in the last step. Also, fuzzy time series approaches can be divided into two main subsets, which are univariate and multivariate fuzzy time series approaches. I'm going to talk about only univariate fuzzy time series approaches in this work. Determining the fuzzy relationships between observations of a time series can be considered as the main part, the most important part of fuzzy time series approaches. In the operations to determine these relationships, on the other hand, it needs very complex matrix operations to determine these relationships. After that, Chen proposed to use fuzzy group relationship tables. It is very easy to use, especially first-order fuzzy time series approaches, but especially when you are dealing very hard to use because of the dimension of these tables. Finally, Huang and Aladağ et al. Proposed to use artificial neural networks to learn these relationships from the data by using artificial neural networks. These are the first studies in the fuzzy time literatures that use machine learning techniques to learn the relationship between observations. I'm going to talk about the algorithm that we proposed before. Aladağ et al. Improved the Chen's algorithm by using artificial neural networks, as I mentioned before. And this algorithm can be given in the 5 steps. In the first stage, universe of discourse is defined and partitioned. The universe of discourse for observations is defined, and for a given length, equal length intervals, U1 to UB. In the next stage, fuzzy sets are defined. Each linguistic observation AI can be defined by the intervals U1 to UB, like in here. Then, in the third stage, observations are fuzzified. It is very easy to do that. For example, an observation is fuzzified to AI if the maximal degree. And in the fourth stage, fuzzy relationships are determined by using feed-forward neural networks. For example, for this fuzzy time series model, in which FT is caused only by FT-1 and FT-2, such a feed-forward neural network model can be used. Only 2 inputs, FT-1 and FT-2. And the target value is FT, of course. In this case, you can see the input and target values in this table. For example, for this learning sample, the corresponding input values of a network will be 6 and 2. These 6 and 2 are the indices A2. So the target value will be the 3. And in the final stage, results are defuzzified. In this algorithm, fuzzification is made by using the middle points of intervals, which correspond to fuzzy forecasts obtained by neural networks in the previous stage. This performance of Alabama University, this is a very well-known data in the fuzzy time series forecasting literature, because in the first fuzzy time series study, Song and Chisholm used these data sets. You can also see the graph of this data in here. How about the selections we made in the implementation? First, second, third, and fourth order fuzzy time series. Algorithm as Huang did, the length of intervals are chosen as 200 to 1000. After following stage 2 and 3 in the algorithm, the number of neurons of hidden layer is changed between 1 and 4, not to lose generalization ability of artificial neural network models. So, for 4 orders, 9 interval lengths, and 4 neurons in hidden layers, totally 144 different fuzzy time series forecasting models are utilized in the implementation. And all of the forecasting results are summarized in this table. You can see the mean square error values obtained for each fuzzy time series forecasting models at the second part of the table. As you can see in this table, when the second order fuzzy time series model is used, interval length number in hidden layers is 4. The best forecasting accuracy is obtained. The best, which means the best mean square error values is obtained. And these results can be compared to other results obtained from the other forecasting approaches, fuzzy time series forecasting approaches available in the literature. So you can see that when you use this model, you can reach the most accurate results from the proposed model. Also, it is possible to examine the results visually. You can see the graph of observed and forecasted values together in this graph. As seen in this graph, it can be clearly said that the fitness between observed and forecasted values is very high. First, maybe we can say something. In order to improve forecasting accuracy, instead of using univariate fuzzy time series approaches, you can use multivariate fuzzy time series approaches. You can use more related time series to get better results. And also, in this study, only a feed-forward artificial neural network model is used. Networks models, such as recurrent neural network model, so you can improve the forecasting accuracy for fuzzy time series forecasting. And these are some references related to this. Thank you for your attention. If you have any questions, you are always welcome. Are there any questions? I think no.
Teşekkür ederim.
Thank you, Professor Hakan Çağdaş Aladağ. If any participants have a question, they can write on the chat box, and we will take the question. If we have, we can take after the all participants' presentation. Now, Dr. Mariam Kavakcı will present.
Thank you. I'm going to be sharing my screen for my presentation now. Okay. I hope you can hear me okay. So I'm going to be talking about neurochaos. I'm a lecturer at Ankara Yıldırım Beyazıt University in the Department of Neuroscience, and I also have 2 laboratories at Ankara City Hospital. So what is the relationship between the brain and chaos? Well, if I had to pick 2 words to describe the brain, without a doubt, they would be chaos and complexity. The brain is made up of more than 86 billion neurons and approximately 125 trillion synapses. So that's the connections between the neurons. And that's in the cortex alone. So thinking about that is really overwhelming. I'm not going to talk about chaos theory because we're all familiar with it, but I did put it in here. The problem really is that this sensitivity to initial conditions makes it really difficult to make predictions in neuroscience for us as scientists who are always trying to predict things, whether it's the climate, stock market, or in my case, brain dynamics. And we do this by deriving models, different types of models. Basically, we just put certain variables into an equation to make any type of prediction and answer our hypothesis. Briefly, we have stochastic processes, which are always random, and then chaotic processes, on the other hand, are highly unpredictable, but some difficult to predict. In chaotic systems, similar to the biological systems that we're investigating, we have something called a strange attractor, and that's kind of that infinity shape that you see there. And the meteorologist at MIT who discovered this in the 1960s found that when he was running weather simulations, when he did implement those slight variations in the initial conditions, the paths, and that's what really a chaotic system is. It's deterministic, and that's what makes it different from totally random behavior. So how much do we really know about the brain? Well, it appears random, but as an analogy, we always use the pendulum in chaos theory. Instead of one pendulum, you can think of each and every individual neuron as a pendulum itself. And if you imagine, almost very, very complex. And the issue that we have in neuroscience is that, and basically in any science area, is that error is inherent in everything. And if we think about p-values, we know that. And given the fact that chaos theory is so sensitive to initial conditions, we know that any tiny little error can ruin our prediction. So it's a very sensitive, hard area that can't be directly observed, and it's really manifested in the system's fluctuations. But like I said, we don't have room for error in chaos theory, and definitely not in neuroscience. So there is empirical evidence, which is why I wanted this to be the topic of my talk today. It's not just theoretical. There is some evidence that chaos theory is definitely in play. In the have shown abrupt switching between synchronous and stochastic random activity in the brain. Random, like cortical oscillatory neural activity, can lead to self-synchronization transitions, which really may serve as a paradigm for this phenomena. And also a mode of self-organization in populations of interacting neurons. So there is some evidence there as well. But the strongest current evidence comes from single cells. And one good example is the squid giant axon. It operates in a resting mode or repetitive firing mode depending on the external sodium concentration. This is much more difficult for ethical reasons to design and try out in humans, but in animal studies we have some evidence. And then between these two extremes, there is this unpredictable settles into an attractor. So I'm trying to make this all relevant to the chaos theory literature. And also networks of cells. For example, in a patch of rat skin, the neurons can distinguish between chaotic and disordered patterns of skin stretching. But what about global brain activity, which is really my area of interest in human beings because of cognition? There's some evidence of that as well. If you think about a slab, overcome the influence, and it's basically, the brain is frozen. When it's hot, there's so much energy that the electron spins are disordered. And there's a critical regime, which is the highest possible dynamic correlations. And the critical state or regime of the brain matters. So why does it matter? Well, it can be really helpful for the brain actually. And not by temperature in my other example. If the balance is tipped in favor of more inhibition, the brain is frozen. If there's too much excitation, it will descend into chaos. And this is where we start to think about mental illness and psychopathology, because really there's a lot of evidence or a lot of room to assume that mental illness could arise from this imbalance of inhibition and excitation. What we need for balanced mental thinking and cognitive activity is analogous to an attractor that we study about in chaos theory. So does the brain actually operate at a critical point? Do we have evidence of this? Not strong evidence, but that's very much possible. And the one clue is the activity of the billions of neurons. And we can measure this with EEG, electrical activity at the different oscillation frequencies. And this is a very common and non-invasive method that we use. And we know that the power of activity falls off as the inverse of the frequency of that activity. I won't go into too much math today. And that was referred to as 1/f noise. And this is the hallmark of systems balanced at their critical point. And this is true for the brain as well. But why chaos? Because we give our brains the kind of computational power we need to process with great speed. So think about a moth that senses the presence of an echolocating bat. It senses the ultrasound source and its neurons start to react erratically. So this mechanism can actually protect the moth who is running away quickly who needs to run away quickly from the bat. And then the most important part, it's definitely not the same thing. Disorder is stochastic, chaos is deterministic, as I mentioned before. But chaos encourages us to think of certain disorders as dynamical diseases. And epileptic seizures are a good example of this. When chaos is not functioning the way it should, this can cause things like epileptic seizures. And this is still work in progress. Chaos might also serve as a signature of brain health, which is researchers report less chaotic dynamics in dopamine producing cells of rodents with brain lesions as opposed to healthy rodents. And this could really have implications in diagnosing and treating movement disorders like Parkinson's disease and other dopamine related disorders. So what's next? I think it's important to explore when does chaos turn into disorder? If this is really a healthy system, what be really mathematically tricky to distinguish between the two, especially in multidimensional fluctuating data like the brain. And for future directions, I think it's important to investigate synchronization phenomena that can give rise to things like consciousness. Consciousness is an area that has been investigated for over a century now with very little progress. I think it's the area in neuroscience that has and I think that could be because people are not really considering chaos theory because it's so difficult to quantify. But it makes a lot of sense if you think about it. So I really hope to see more work in this area in neuroscience. Obviously, evaluating the contribution to neurobiological mechanisms during disease states is going to be very important. Predicting neurological profiles, genetic disorders of the mind, and psychiatric illnesses. So as a summary, data suggests that cognition may be related to chaotic brain processes resulting from random chaotic disorganization. And these changes in chaotic dynamics might represent specific characteristics of dissociative states and chaotic-like cognition in mental illnesses. Nonlinear dynamics and chaos theory may help us understand the neurobiological mechanisms that occur in both healthy and pathological states. So I really am excited to see the future of this area of work, and I think it holds a lot of potential for solving some of the issues that we have currently. Thank you very much. And I can take questions whenever, if you have any.
Thank you, Dr. Mariam Kavakcı. It says that both presentation are, because of my field, it's quite different and also interesting for me. I partially understand part of some of the parts, but it's obviously very great presentation. Thank you.
Thank you.
Our last speakers will be Professor Renato from Brazil. Professor Renato, could you hear me?
Yes, I can.
Okay. Now it's your turn.
Okay, thank you so much. Let me start my presentation then. I don't think I'm doing it right. I'm doing something wrong. I don't think my PowerPoint is not responding. Sorry for that. Do you see it or not?
Yes, we can see it right now.
Okay, great. So, first of all, thank you so much for the kind of invitation of Professor Schuller-Resting. And it's a pleasure to be here with you in this very interesting symposium about developing leaders for a complex world. So I will begin with a short introduction, talk a little about deep learning, and then come to an issue that I think is one of the most important, an example for difficult issues, difficult challenges for the future leaders. So this is the connection with deep learning. Okay. Still, as Heraclitus said centuries ago. And yet, this is not more or less true than today, as big changes are coming all the time and faster and faster. And this causes what Toffler said is future shock, that is diagnosed as a new and inevitable widespread psychological illness in the sense of a social paralysis induced by rapid and accelerated technological change. As a consequence, some individuals pray for the return of the old good times, but I'm afraid to say that there is no coming back. There is no coming back for the old good times. As an example, Kodak did not take it seriously and lost an entire market it previously dominated. And also, Nokia cell phones, Sony's Walkman, and examples of companies that lost their dominant market positions. And of course, many things we are so used to use now were in another time seen as just science fiction. And of course, many of those things, a few of them may not make through, but even if just a few of them succeed in doing it, they will have a. So by that I mean that future leaders are being challenging from a very different world than today, and they may need to be prepared for it. Let me introduce the idea of deep learning. As I already know, deep learning is based on a hierarchical network of neural nodes, each data. And this deep learning then produces due to this hierarchical network, an increasing complex and more complex model of the data, so that when you input lots of pictures of dogs and cats, for example, and other animals, he is able to learn, develop features and between dogs, cats, and other things. This thing is more interesting when you go deep and look at the working inside the various layers in which these neural nodes are arranged. For example, if you introduce a portrait of a person, then in the basic levels, the system, the model, just between bright and shadow zones. As the model progress through the various layers, some combinations of edges, some features in the original picture are being recognized, and I emphasize, recognized by the system itself, is not programmed by the coder. And at the end, the model is so complex that it's able to identify one person in a face recognition system using by the policy. Now, things become really interesting when you go from visual to other kind of problems. For example, theorem proving. Yes, deep learning is being used to theorem proving problems. The idea is the same. You provide the system with many theorems and their proofs, and the layers start finding structures in these proofs. And this is quite disturbing because the features, the structures that are uncovered by the system in this process sometimes are not known by the mathematicians. I mean, the system is developing some kind of alternative mathematics, including some structures that doesn't know. So in a sense, deep learning is somewhat teaching us a new kind of mathematics. And this is probably some future ahead. And this will make a question for the future. Can be an artificial intelligence system alive? Well, John McCarthy, in the old days of the beginning of the artificial intelligence, no one will call it artificial intelligence anymore. And probably also know that Sophia AI was even granted Saudi Arabian citizenship. However, I must say that I have seen it working in person, and I'm quite not convinced yet. But it's an interesting perspective for the future. So this is the question: intelligent system be alive? And that poses a even more difficult question, such as, what is aliveness anyway? Well, and then my friend Melanie Swan provides with another interesting idea. She doesn't simply oppose intelligence and human. She proposes the idea of a wide spectrum to autonomous agents and even teammates. So running from high frequency traders, you know, those bots that are dominating the stock market now, assistants like Alexa and chatbots, autonomous devices such as Zomba, a autonomous car, and then comes enhanced humans, people using wearables and also brain-computer intelligence. Musk. And then will come biological robots and even empathetic sentient machines. So yes, we are moving from artificial intelligence to artificial sentience. And then comes the ethical question. Should we talk about the ethics of multi-species intelligence? Think, for example, the caused mainly from those bots of the stock markets. Or also the car accident that is a Google self-driving car occurred some time ago. Can a system, IA system, be held accountable for its actions or its coders? And think about an enhanced human. Which part of it should be blamed? The artificial? So this is just to raise the question that the ethics of multi-species intelligence is just one interesting question, interesting challenge that our future leaders must face in the near future, the complex future we are coming in. So, for the education of its future leaders, as you know, present education system is based on the first industrial revolution that aimed to growing factory workers out of farmers' children. Now, because of that, the vast majority of the leadership program now is classroom taught, chalk and talk, rationally based, individual focused methods, and failing, as Roland educated to see disturbance as dysfunctional. Leaders now must learn to view disturbances as transformational. So, an inspiration for this education for future leader model comes from the also called Industry 4.0 that happened in Hanover Fair a few years ago. This model of industry that was presented there is based on artificial intelligence, distributed consensus, that is the technology on it, blockchain technology is based, combinations of hardware, software, and biology, coexisting multi-species intelligence. So this 4.0 education model suggests should be based in project-based field experience, mentoring, and anywhere, anytime, continuous and be more focused in data interpretation than memorizing and calculation, and of course, on intense update in all these cutting-edge technology. So please don't hesitate in contacting me through my LinkedIn account, and thank you. If someone want to do some question, please go ahead.
Dear Professor Renato.
Hello.
Hello. Thanks for the presentation.
My pleasure.
I think we don't have any questions from the chat box, but I have, it's a good thing to be moderator in the sessions. I am using my advantage always to ask questions to the presenter.
Of course, yes.
I have two questions actually. As I mentioned just before you, I will ask questions, depends on how much I understood from your presentation. It's quite informative, but I would like to ask a few questions. My first questions would be to you, Professor Renato. You mentioned about the artificial intelligence and
Yes.
technology. I would like to ask, it's not very technical questions, but I'm super curious about the artificial intelligence technology and the chaotic system, the feedback system within the chaotic systems, which is positive and negative feedback systems within the chaotic systems. Within this artificial intelligence technology, how does the feedback system would work within this artificial intelligence and such kind of technologies?
You talk about this neural network that works in deep learning.
Mm-hmm.
Yes, it's quite interesting because, you know, the progress of the model building goes forward and backwards many times. And each time it does this epoch that is so called, the system interacts, you know, these models have hundreds of parameters. And so going forward and backward produces more interaction between these parameters. So the model becomes complexer and complexer, even more. So the fascinating thing is that this is such a complexity that you can't not understand it from just looking at it. So it becomes quite a black box. That's quite disturbing, you know, because as I said, when you look for a visual analysis, you can understand some features, some the ears, the nose. But when you go to something abstract, so for example, mathematics, what is that is emerging? What are those features that are emerging mean? We don't know. It's some kinds of mathematical structure that are being uncovered by the computational system. That's quite makes us quite uncomfortable because, you know, hundreds of years of mathematical evolution is somehow being challenged by some black box of artificial intelligence. Is quite disturbing, in my opinion.
I agree with you in some point related with this artificial intelligence. That's why I was curious about how the feedback system will be work on this neuron technology, because it's I found it much more complicated and too much uncertainty over there, I guess. Thank you. And my other question will be for the Dr. Mariam Kavakcı. In your last slide, you mentioned that the future direction in the field related with the cows. And how do you see the development of the application of chaos theory in your field? Do you think there will be much more popular in the soon, or it will be still too much black box like Professor Renato mentioned?
Well, you know, I'm a physics teacher, and I'm sometimes quite frustrated. Sorry?
This question for Mariam Kavakcı.
So sometimes I find it quite frustrating because, you know, the traditional physics teaching passes to our students the idea that the world is quite a mechanism, a predictable, deterministic mechanism. And all the exercises we run in class are just mechanical, just predictable. But we know, and as the most presentations here show, nature, the real nature, is far from classical, is far from deterministic. So I believe most systems we know are indeed chaotic. And yet, I have never learned about chaos system, chaos theory in all my graduations. I don't know. I have a doctorate in physics, so I have never heard about chaos system. So we are building in our formation some kind of artificial world where everything is so easy, so simple, but that's not true. So I hope that of the formation of our students in the near future start to contemplate more chaos theory, because in fact, this is the most useful tool we have for our future to understand your nature and your world.
Dr. Mariam Kavakcı, your microphone is off right now.
Okay, I can add something to that as well. I think that's a great answer. And I think with the advent of supercomputers and the advancement of technology, that especially in neuroscience, this field will be much more feasible to investigate. And I think a lot of the limitations that we have had is because of that. So I think if we work collaboratively with physicists, computer scientists, statisticians, neuroscientists, then at least in my area, I know we'll move forward much faster. It's just that type of collaboration hasn't really happened the way I would like to see it. And so I'm grateful for conferences like this to, you know, bring awareness to the different areas and how chaos theory can really apply and how we can all from different fields work together. So I do think that there's a bright future for neuroscience in this area, as long as we collaborate and leverage the technology and the knowledge from our colleagues.
Thank you. I just checked the chat box. There is no questions. That's why I would like to, coming to the end for this sessions, I would like to thank each of our privileged professors here who contributed to make such a great invited speaker sessions. This sessions also was live on the YouTube as well. We will put the link on our website too. You can watch it later. So thank you very much, Professor Çağdaş, Hakan, Aladağ, Professor Renato, and Dr. Mariam Kavakcı. Once more, thank you for accepting our invitation to be our invited speaker here.
Thank you.
Thank you. It's my pleasure. Thank you.